So, what is ensembling? Ensemble learning, or more commonly known as ensembling, but it's the same thing. It's the process of combining several predictive models in order to produce a combined model that is better than any individual model. In other words, I take 3 models. They're all at 70% accuracy. I combine them, and magically, the ensemble, which is the 3 models put together, has 75% accuracy. And you're like, where did that 5% come from? All of my models were at 70%. But that's the beauty of ensembling. How do we do it? Well, usually it's a really simple process. If it's a regression problem, meaning the output is real valued, you just make your predictions and then you average them. Okay, that's it. For a classification problem, there are 2 common ways of combining them. One is to let the models vote, meaning all the models make all the predictions and they vote on, which prediction is the best. Sorry, that's not a good way of explaining it. If like model A and model B say Mexican and model C says Italian, then you go with Mexican because 2 of the models said Mexican. Okay. An alternative way that tends to be better, in my opinion, is to just average the predicted probabilities. And we'll come back to what that means below because that's what we'll do. Okay. Now, for ensembling to work well, models must have the following characteristics. Number 1, they have to outperform the null model. Okay? They can't be so bad that they're worse than guessing. Okay? And number 2, they are ideally as independent as possible, meaning their predictions are generated using different processes, such as different model types, different features, and different tuning parameters. In other words, you could create 3 models that the only thing you change about them is like the number of n neighbors, and you could ensemble those, but that's not going to do very well. Yes, you've changed a tuning parameter, but the models are very similar. Ideally, you want to create completely different models. One that uses text features in a naive Bayes model, one that uses numeric features in a KNN model, one that uses this stuff in a logistic regression model, and you combine them all together, and it tends to be that the more different they are, as long as they're still accurate, the better your ensemble will be. Okay? So here's the big idea that kind of explains why that works, okay? Why it's not so magical and it kind of makes sense. If you have a collection of individually imperfect and independent models, the one-off mistakes made by each model are probably not going to be made by the rest of the models, and thus mistakes will be discarded when averaging them. In other words, as long as each of the models is pretty good and they think differently, you can put them together and the majority is going to be smarter than any individual model. So you'll let the majority kind of take over the actual prediction process, and you get a better overall predictions than any one model. Okay? Let me just say, there are models that have built-in ensembling. Random forest is a famous example of that. So we're not talking about models that have built-in ensembling. We are talking about ensembling that you do on your own. Okay? So that's kind of the high level on ensembling. Let's go ahead and do that. You'll find it's not actually very complex in contrast to the material above. So let's start. So we're going to use 2 models. Okay? We're going to build a KNN model using only manually created features. And then we're going to build a naive Bayes model with the text features. Okay. So because I haven't built this model in this notebook, I have to redefine it here. So I'm defining X as my two numeric columns, and my Y is the cuisine. Okay. I'm going to use KNN with K equals 800. And the reason I'm doing that is in the last notebook, that was the best performing value of K. Okay. So we've instantiated our model. Then we're going to train it on all of the training data. And then, of course, we need to define our X new, and that's the manually created features from the new data. And now, rather than making class predictions, we're going to calculate predicted probabilities of class membership. Okay? So, what that looks like, well, actually, let me run it, and it's easier to talk about it if you're not familiar, if I can give you an example. So instead of saying knn.predict x new, I say knn.predict proba x new. Okay? And you'll see that it makes, for every observation in the test set, in the new data, it comes up with a predicted probability that that observation belongs to each class. Okay? So I'm going to take that. I just want to show you these predicted probabilities for the first row. Okay? And when what you see here is essentially like, okay, we predict that for the first observation, the likelihood it belongs to the first class is 2.6%. For the second class, it's 2.7%. For this class, it's 1.3%. And this is essentially, if you know how KNN works, this is essentially just what percentage of the 800 nearest neighbors belonged to that class. Okay. Now, I'll go ahead and display the classes zipped together with the predicted probabilities so that you can see them together. And basically, our model for every single observation has figured out numbers like these. And in this case, the most likely class is Mexican because it had the highest percentage. Okay? So normally if I had said .predict, it would have just said Mexican. But I said .predict proba, and so it shows me predicted probabilities of each class. Okay? And to be very clear, the predicted probabilities will sum to 1 for each row. Okay? So if you had a 2-class problem, it would have said something like class 1 has a probability of 0.7 and class 2 has a probability of 0.3. It'll always add up to 1. And in this case, there are 20 classes, so the numbers are just a lot smaller individually. Okay? We've calculated predicted probabilities from the KNN model. Now, we are going to calculate predicted probabilities from the naive Bayes model. Now, if you recall, we already created a naive Bayes model with the text features, and it's stored in this rand object from before. And all we need to do is do rand.predictproba x new, but x new has to be the ingredient text. Okay, so I'll go ahead and run that, and then we'll calculate our predicted probabilities, and just like above, it's 9944 by 20. Okay, 1 column for each class. So just to show you, like, these are its predicted probabilities for the first row only. Okay, so again, there are 20 classes, and it makes a predicted probability of each of those classes. So how do we ensemble them? It's actually super easy. Okay, if I just wanted to ensemble one row, I would actually just add the row from KNN plus add the row from this randomized search CV, I would literally just add them and divide by 2. Okay? And this is the ensembled predictions from the 2 models for the 20 classes. Okay? So you'll notice that, and you could go back and you can check the numbers, this number is just the average of this number and the first number in the model above. Okay? So that's how you average them for just one row, but it's actually just as easy to average them for all rows. Okay? So if I just add those 2 objects and divide by 2, okay, and I'm actually going to put them in a data frame so we can look at them. All right? So when I do that, you can see that for observation 0, here are the predicted probabilities for each class. Okay? For observation 1, here's the predicted probabilities for each class. So I've averaged my predicted probabilities to actually make a prediction. All I need to do is figure out which column has the highest number for each row, right? So for this row, it turns out British is the highest. For this row, I'm not sure which one without scanning it, but you just need to do that for each row. How do we do that? Well, I just used a little trick. There's a NumPy function that I can apply across the y-axis that says figure out what column has the highest number for each row, and I'll apply that function, and what you'll see is that, in this case, it's British that's the highest number. In the second row, in row 1, it's Southern US that has the highest number. In the third row, it's Italian that it has the highest number, and so on. Okay? So there's probably other ways to do this, but I think np.argmax is a nice way. And finally, there's nothing else to do other than just create a submission file and submit it. And you can try submitting it. Here's the score you're going to get. Ensembling, for what it's worth in this case, actually made the performance get worse. And the reason for that is that our KNN model, if you remember, is actually like barely better than the null model. And in fact, it's so bad that just the randomness of it is, causing the results to go down. Generally speaking, you don't want to put in really weak models into your ensemble. You want at least decent models, okay? They should be better than null, and it shouldn't be a question as to whether they're better than null. They should be a meaningful amount better than null. Now, I used it in this case because I'm trying to teach you a process, not because this was an awesome technique for this problem. But in general, this is how you do ensembling. Now, by the way, I have 2 side notes here. One is you could have done a weighted average. I didn't have to weight these equally. I could have said KNN plus 3 times new pred prop rand and then divide it by 4. So I could have done a weighted average. And that's often a really simple way to tweak your ensemble and make it better by specifically emphasizing the model that you think is the strongest model in the ensemble. And this actually works quite well, okay? So that's one little side tip on ensembling, okay? The other side tip is that in Scikit-learn 0.17, there's a new class called voting classifiers. Now, I expect that Scikit-learn 0.18 is going to provide even more functionality like this. This is just Scikit-learn kind of dipping its toe in the water of ensembling and how to ensemble separate models. So voting classifier actually makes it easier than what I've shown you above to ensemble classifiers. However, its one limitation is that it only works in the case in which all of the classifiers are fit to the same data. So the fact that our two models used different pieces of data, made it so that I can't use voting classifier. Voting classifier instead is better when like I have a single set of data and I want to run a naive Bayes model on it, I want to run a logistic regression model on it, and I want to run a random forest on it, and I want to do an ensemble, and all of that can be accomplished in like two or three lines of code. Okay, so voting classifier makes it easier, but it only works if all of your classifiers are being trained on the same data. Okay. Amir asked a great question. How would we decide the appropriate weights? And my experience is you just try something, and then if it gets better, then you keep increasing the weight of the model you increased its weight. So first try, pick one arbitrarily and weight it higher. And does your ensemble get better or worse? And if it gets better, go ahead and increase the weight further and further and further till your ensemble starts getting worse. That's one way to do it. You could also think of a way, if you want to be really systematic, you could kind of do a grid search, and voting classifier might even allow you to do a grid search of weights. I'm not sure on that. I think it does. But experimentation is the short answer for that. Great question.